Hi everyone, my name is Lydia and this is what I wish they had taught me about econometrics and introduction. In the previous video, we covered 5 matrix tricks that power almost every OLS derivation. In this video, we're going to cover 5 more of these tricks, but they are the ones that actually reveal the geometry and the structure of OLS. Let's start with the very first one, which has been a concept that you have seen in the proof of the OLS, but also is like properties of this X prime X matrix. So X transpose times X is always symmetric. It's a very nice math part, let's say, of that we can use in econometrics. The reason why we can see that X prime X is symmetric is by doing a very quick proof using the tools that we have introduced in another video in this playlist. So if we start with X prime X, so I'm just calling it prime, keep in mind I'm referring to the transpose, all of it transposed, that means that the first one should be a transpose of the transpose times X transpose. So we're reverting the order of the two, but we are also transposing the second one. Okay, so that means that ultimately what I will have is just the transpose of the X times X. So we're simply reversing the order in a sense, because the transpose of a transpose should give you back the original matrix. Why does this matter? Like, why does this trick or this property matter? It's because symmetry makes it a lot easier for the math. It means that we have fewer parameters that we need to estimate, and it makes derivatives a lot more simple. It might not be very obvious how exactly the math is simpler in the OLS bit, but when we get to more complicated methodologies like the GLS and formulas used for the variance, it's going to become a lot more easier. For now, let's move on to trick number 7, which is the fact that this X transpose X matrix is positive semi-definite. And this is a very, very important property of this matrix, which means if we take any, let's say, vector v, so for any vector v, we can actually show that the transpose of v times x prime x in here times v. So if you notice, I have added the transpose here of the v and v as it is to kind of envelope this matrix. This is going to be equal to xv transposed. So we are kind of reversing back to using that transpose trick times xv, and I'm just grouping them together. If you notice, this is the quadratic trick that we showed in the first video, because inside the brackets, basically, we have exactly the same thing, x times v, but it's x times v transpose times xv, which means that ultimately what we have is xv, and I'm going to put here the absolute values, squared. All of this is greater or equal to 0, because the squared norm can never be negative. Now, what is the meaning of this expression? Or like, what is the meaning behind having such a property? Is that actually there is no direction in the regressor space that would produce negative energy. Think of it this way. And what that also means is that the geometry is stable and well-behaved. Also, if X has a full column rank, like we have mentioned in trick number 5, this squared length is 0 only when the V is actually equal to 0. So that's when your X prime X becomes positive, definite, and invertible. Okay, so let me just write that down because it's quite important. So if X has full column rank, then this xv squared is going to be 0 only when V is actually equal to 0. Okay. Moving on to the eighth trick, the projection matrix properties. This is a very important, and it's, let's call it like the superstar of matrix of the OLS. If we start from what we already know in terms of the fitted values, we know that the fitted values are equal to x times beta hat, the moment that we have estimated it, and we know that by substituting the actual formula of the beta hat in here, we are going to get that y hat is equal to x times x prime x minus 1 here, x prime y. This entire block makes what we call our projection matrix. And that's why we can rewrite the whole thing as the fitted values being the projection of our y variable. Keep in mind, this is a direct interpretation of that nice graph that we have in space of the projection of the y, because the y basically drops into a space spanned by the columns of x. Now, the magical property that we have, that where p square is equal to p, is a derivative in a sense of that concept of what the projection matrix actually identifies, because projecting twice shouldn't really do anything to what you're doing. So again, the projection of a projection, it's still your projection. And that's why we call it the projection property. Moving on to trick number 9. This is the residual maker matrix. So now we're introducing a little bit a new concept to you guys, and we will call these residual maker matrix M being equal to the identity matrix minus the projection matrix. Keep in mind, the identity matrix is a matrix where the diagonals is all ones and everything else is zeros. Okay? Now, if P gives you the fitted values, the matrix that will give you the residuals is going to be this M matrix, basically. So this gives you fitted values. M is going to give you the residuals. And let's check very quickly how exactly it does it, so that you don't just remember it as a rule of like, okay, this relation is what is giving me the residuals. So if we multiply the residual maker matrix to our y variable, then what we will get is the identity matrix minus the projection times the y. We distribute the product in here, so we're going to have y minus p times y, but we already know from the previous trick that p times y is your fitted value, so ultimately you have y minus the fitted values, which we know by definition, and also from the very first few videos that where I have introduced you with the jargon on econometrics. This is simply residual. Either the Latin letter E or the Greek letter epsilon here with the hat, whichever it's the notation that you are most accustomed to. So M is creating the residuals in one step. It's in some sort of way another projection, but you do it into the orthogonal complement of the X. Keep in mind, I have not written this here in the tricks, but this is for an extra for you to remember. The residual maker matrix has the same property of the projection matrix, where M square is exactly M, because it's a projection into the residual space. Lastly, trick number 10, which we have seen quite extensively throughout all of our videos when talking about the OLS. It's the orthogonality condition, which we have in matrix notation written as X transpose times the residual equal to 0. So this is where the geometry meets the OLS solution. meaning using the normal equations, our x transpose times y minus x beta. Keep in mind here, this would, once we find the derivatives, would be our beta hat. So this is equal to 0, and ultimately we've got simply the x transpose times e equal to 0. So every regressor is orthogonal to the residuals. So these 5 matrix tricks have described the geometry of OLS, and they are in attachment to the previous 5 tricks that we showed you behind the mechanics of the derivations. Hopefully, this will give you a full set of tools that you can use to follow more easily your lecturer or class teacher, or also to give you a bit more confidence when you read through either the Green or the Wooldridge book, if you want to get more knowledge on the econometrics world. I'll see you in the next video.